TUBS-IRMB. Digital India. Educated India.
Welcome to this fifth lecture, a fifth GIAN lecture in high fidelity lattice Boltzmann methods. Today we're actually coming to the lattice Boltzmann method, or slowly the first step in this by using the discrete velocity model. So, and for this we have to recap a few things from yesterday, because as I said in the end, we depend on that particular limit of the BGK equation. So we get the Navier-Stokes equation, and because there was people saying that my Navier-Stokes equation was dimensionally inconsistent, which, you know, depended on what is rho. Now I put a rho with this asterisk, meaning the rho as you know it, so kilograms per, the density of the fluid, kilograms per cubic meter, into the time derivative of u plus u dot nabla u is equal to minus the gradient of the speed of sound squared times the density plus tau times the speed of sound square times the density into Laplace u. So I got rid of this bulk term, because we are assuming that the divergence of u is here 0, yeah. And now we call this here the pressure, and we'll call this here the viscosity. So there is an equation of state involved here. This is the speed of the pressure is the speed of sound squared times the density. So the speed of sound squared is related to the temperature. So basically what the Boltzmann constant is just the translation between energy and temperature, in a sense. Yeah. Okay, this is not quite accurate, because energy density, because energy is an extensive quantity and temperature is an intensive quantity. So there is a little bit more to it, but not much. So this thing here is the mass of the particle times the density of the particles, the number density of particles. So the Mach number, we have seen this, is of course u divided by the speed of sound, and therefore the speed of sound is always proportional to 1 over the Mach number. This tau, the mean free path, is related to the Knudsen number times the Mach number. So tau cs squared is proportional to the Knudsen number divided by the Mach number, and this Knudsen divided by the Mach we just redefine as 1 over the Reynolds number. And the Reynolds number is usually defined in fluid mechanics in 2 different ways. So it's the velocity scale times the length scale divided by the kinematic viscosity, or you may be more familiar with it being the velocity scale times the length scale times the density divided by the dynamic viscosity. So this is the Reynolds number. And the dynamic viscosity is, in written mu, is the density times the kinematic viscosity. So the kinematic viscosity is this mu. And this again is tau Cs squared times rho. So mean viscosity is mean free path times the speed of sound. Yeah. So this is diffusion. If you learned about diffusion, this is how diffusion always works. So there is a velocity with which particles do their random walk. Yeah. And then there is a time until they. So there is a time for which they go forwards until they change their direction in a random way, yeah, and this together gives you the diffusion coefficient, right? So you can also say that tau times the velocity is the distance. So this is equal to saying that the diffusion coefficient is the distance that a particle travels, yeah, times the speed by which it travels. Yeah. Okay. Just writing this down for the afterlife. Velocity scale. L is the length scale. And this nu is the kinematic viscosity, which is a proper diffusion coefficient. A proper diffusion coefficient always comes in square meters per second. I'm very sorry that we use so many letters that all look the same. Now we have V, nu, upsilon, yeah, all look the same. Yeah, I try to keep them a little bit apart. So we got yesterday the Navier-Stokes equation from the Boltzmann equation. You see, my R's also look like a V. Sorry, yeah, and we derived this under this assumption that the Knudsen number is larger than 0, but the Knudsen number square is 0. So basically, it's a low order approximation in Knudsen number of the Boltzmann equation, if you will. Yeah, first order approximation. Yeah. So this is now important, as I told you, because this determines what we have to keep about the kinetic, what amount of kinetic information we need in order to solve the Navier-Stokes equation. Yeah. And if you want to solve something beyond the Navier-Stokes equation, obviously you would have to have more. I mean, like you know that the Navier-Stokes equation breaks down somewhere, but this is here when. So the reason for this is that you potentially need more. But I mean, getting a little bit off rail here. Of course, if you really want to have discontinuities in the flow, this can become a little bit tricky because a discontinuity is potentially not well represented by a continuous function, and therefore there may not be a convergent, this may not necessarily converge in Knudsen numbers to resolve your discontinuity. Yeah, this is why it, after the Navier-Stokes equation, it actually becomes difficult to describe these higher order terms in a continuous fashion. And then you would be better off starting with the Boltzmann equation itself rather than trying to develop the Boltzmann equation to higher orders. Okay. So our observation here is we have Knudsen numbers that is small but finite. Another thing we want to take into account is that for our engineering problems in particular, we have a finite Reynolds number. Yeah. So we saw that if we make tau smaller and smaller and smaller, yeah, what we get is actually the Euler equation. And the Euler equation is something that you get if you go with your Reynolds number to infinity. Yeah? So we see in the Navier-Stokes equation, yeah, this tau cs square is 1 over Reynolds number. Yeah, so this is in the Navier-Stokes equation. So basically, for infinite Reynolds numbers, we have no diffusion, and we go to the Euler equation. But this is not what we want. In engineering practice, we want to solve problems with finite Reynolds number. Yeah, so finite and actually for specific, I should say specific maybe. Yeah, specifically fixed Reynolds number. And the Mach number should scale as the Knudsen number. So, yesterday after the lecture, I told you a little bit that the Navier-Stokes equation can easily fall apart. And for this, you may think about re-entry of spacecrafts and something like this, very high and rough height gas and so on. Yeah. So there it's clear this small Knudsen number thing falls apart, but there is also there's also the very simple things that you can observe in this room. So there's this water dispenser. If you open the tap, yeah, water drops out, and the water that is dropping out, this will combine. Yeah, this will combine so with the water in the basket below. So say there's water in the basket below, and here's droplets, and they are coming down. Yeah. So what, according to the Navier-Stokes equation, they should do is they should bounce off and bounce forever. Yeah. Because so there's a droplet. Because if we zoom into this, we have, and this is falling down, we have here gap, and say this gap has the length L. And for this, what the Navier-Stokes equation predicts is, what am I writing? Navier-Stokes equation predicts an infinite pressure as the gap gets smaller. And because of this pressure driving everything apart, no merging, between droplets and water in baskets is possible. This is according to the Navier-Stokes equation. And if you are a big believer in the Navier-Stokes equation, so I've seen, as I told you yesterday, I've seen mathematicians actually insisting on that. Yeah. So, in fact, there is, there is a paradox that if a plate lies on the floor of the ocean, you cannot lift it, because if you try to lift it, the force would be infinitely large. Which is, of course, nonsense. I mean, you have a water column on front of it, and the atmospheric column, yeah, you multiply this by the area, yeah, so pressure, and then you have the force that you need to lift this, yeah. So this is a physicist way of thinking. But according to the Navier-Stokes equation, yeah, you try to produce a gap. So your Poisson equation tells you that the pressure goes to negative infinity there, yeah, and that it is completely impossible to lift this. The problem is pressure in principle cannot go to negative infinity. It cannot go. It physically cannot go negative. So if there's you can only have pressure on one side and vacuum on the other side, right? And then you are done. Then Navier-Stokes equation has no validity anymore. Yeah. Okay. The thing here that's the point is, of course, that this is only true if L, so you can use the Navier-Stokes equation only if L is much larger than the mean free path. And for this, you basically so I mean when the water surfaces, when they get closer and closer, then finally we'll have the condition that lambda is larger than L, and then there is, of course, no Navier-Stokes equation anymore. Invalid. So question. Mean free path of air. Any idea? Standard pressure. I mean, there's an interesting thing. In Albert Einstein, in 1905, he did a lot of stuff that is quite interesting, and I think there is one paper that's pretty underrated. That was on the Brownian motion. And the interesting thing about this Brownian motion, that this was the final blow of the idea that we have a continuous world. Yeah, so actually in this paper he explains that the Navier-Stokes equation actually is not scale invariant, or the diffusion equation actually, yeah, but doesn't matter, it's the same thing. So the diffusion equation is not scale invariant, yeah. So due to this diffusion effect, there needs to be a finite scale. There needs to be a finite scale, and this finite scale he could calculate just looking at the known diffusion coefficient or the known viscosity. So from the viscosity of the air, he could determine, out of his, armchair, not the size of a molecule, but the distance that a molecule would travel before it hits the next molecule. Because this was the big question. So if there are atoms somewhere below them, how large are they? Yeah? And Einstein discovered that, you cannot decide the size of the molecules themselves, but you can decide the distance that they would travel. You can measure the speed of sound. Yeah, that's easy. And you can measure the viscosity, and by measuring the viscosity, you can measure this distance. So now he came up with a number here, which is roughly, out of his armchair. Yeah. So what is this number? Any idea? Give me a number. 10 to the minus 8. Yes, it's correct. It's 16 nanometers. So you see, that's pretty small, yeah? So this is how small you usually need to get in order to see the Navier-Stokes equation breaking down. So the Navier-Stokes equation indeed is a very good approximation for a lot of problems, yeah, for a lot of length scales that we are interested in. Yeah? It's just that you also have to keep in mind you can get, things, when they get closer, they can get closer than 16 nanometers. This is one thing. And the other thing is that this length scale is inversely proportional to the pressure. So if you lower the pressure this by 100 times, this gets 100 times larger. And then, 6 microns is not so small anymore, actually. Yeah. So 6 microns is almost, if you have a very, very thin, not me. If you have very, 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 very thin hair, yeah, then this could already be in that range. Almost. So, speaking about history. Now let's look about the Navier-Stokes equation again in moments. Which we have written down already, dt, now this would be m100 is equal to minus dx m200 equilibrium minus dy m110 equilibrium minus dz m1, dz11 equilibrium, and then we had plus tau 1/3 dx x m300 equilibrium. Okay, it's not fitting anymore. dy m2 this is the second. No, it's 1. Okay, help me. It's 120, right? Yeah. So So how would we know? We are taking the second derivative in y, so we have to count up. So we start with we start with 100, so we have to count up y twice. So it would be m120. So and here it is. We have the second derivative in x. So we count up the first index by 2. So and then the last one would be counting up the third index by 2, and all of these are in equilibrium. Yeah. So now from the analysis that we did yesterday, we concluded that the highest moments in the Navier-Stokes equation that we need that we need for the Navier-Stokes equation are M300, M12, M102, yeah, and of course the permutations thereof. So the things that are third order. These are the things that we need. So this means if we want to solve the Navier-Stokes equation using the Boltzmann equation, then an approximation sorry for not writing, approximating the BTE up to third order moments is sufficient for the Navier-Stokes equation. It's always disappointing for people who are learning the Boltzmann equation, the Lattice-Boltzmann equation, that it is really a Navier-Stokes solver, yeah, and not a Boltzmann solver. Yeah, sorry if you came for a Boltzmann solver. It is a Navier-Stokes solver. So let's build a model that does this. So we want to have a discrete velocity model, and because we are lazy, we start in one dimension. And what helps us with understanding the dynamics of this is this so-called characteristic diagram that looks like this. We have one space dimension, and we will use the same diagram also if we use more space dimensions, but then we will only show one of them, right? Because we try to draw on paper, yeah? Because we have a space dimension and we always have a time dimension. And now we discretize both. So we say that this distance here is 1 delta x, and this distance here is 1 delta t. And now we have here our lattice nodes in space, and we also have them in time. And they must now be connected via velocities. Yeah? So these things are moving through space and time. Now, if a particle has no velocity, it will stay where it is, like the one that I've just drawn. Yeah? So it will move just in time, just along the time direction, but not in the space direction. Whereas a particle that has the velocity going to the right will move in space and time like this. A particle that's moving to the left will move in this way. Yeah. So now we have all of them. So all of these nodes have particles or particle directions that go to their neighbors. Okay, so the idea behind this discrete model here is that you are moving in one time step one grid spacing, and you have a velocity c. Yeah, so c again is delta x by delta t. So I have to admit there is we also use c as an index, but right now we are using only one dimension, so we'll have only one index, so no collision here. We call this c the lattice velocity. And in order not to collide with our indices, and in lattice Boltzmann, it is anyway common to write all of this in so-called lattice units, which is pretty lazy and for somebody who is teaching physics, always a problem. Yeah. So imagine you are a guy who is teaching some physical stuff and you're doing some numerical stuff. So then you go to one class, potentially you have the same students in front of you, and you have to tell them, always do all calculations with proper units, right? And then you come to numerics and tell them, computers don't know about any units, you have to calculate with numbers, yeah? So now you need, either you compromise somehow, or you just accept you come to this class and suddenly you write down equations that are on the face of it physically inconsistent with their unit system somehow, yeah? So because what we are going to do is we are assuming that delta x equal delta t, so is equal to 1. So physicists, yeah, impossible, but you know, on the computer we just deal with numbers. It is important for the equations that we write, that all the terms, pressure and velocity, are given in lattice units. In this lattice units, delta x by delta t. Yeah? So I've seen people making this mistake, implementing lattice Boltzmann. Didn't work. I tried, and I looked into the code, everything looks fine. So then I noticed the way they calculate velocity. And so they calculate, so they see velocity, they think velocity is meters per second, so they introduce their physical velocity. So maybe you get along with this in finite elements or control volumes, yeah. So you can deal with your physical velocity in your calculations. By the way, which you should never do, never, even not in finite element, even it's possible, because this is most likely not numerically very, very stable. Yeah? So you would always try to normalize your velocities to something that fits to your discretization. However, in lattice Boltzmann, it only works when your velocity is given in delta x by delta t. Because this assumption, it's moving one grid spacing in one time step. Now this is built in. Yeah? So, in this picture, as I draw it, we would have 3 discrete velocities. So our Xi, so you know, I is, we have I as an index of the 3 different velocities is I times c, and this is I times delta x by delta t, and I in this case being an element of -1, 0, and 1. So they can move with velocity -1, with velocity 0, and with velocity 1. And now the algorithm proceeds like this. We have a so-called streaming, where particles move with IC is equal to IC delta x by delta t I integer. Okay, so you may have more speeds, but the speeds need to be integer because they need to come from one lattice node to another lattice node and not as anything in between. You had a question. If you have a question, please use the mic.
Sir, can't particle move along only x direction?
Particle move?
Only along x direction. Yeah, you are
Yes,
saying that?
yes, it can only move along x direction because we said in the beginning that we're dealing with a 1D problem. Yeah. So if we it doesn't make sense to solve the Navier-Stokes equation in 1D. So later we have to add more directions.
So then there might be 2 more directions possible, right? Like you're saying 3 directions were possible to minus 1, 0 and 1.
So so there are
Like,
infinitely many possible. They can just move faster.
okay, then why are you taking only 3 directions? Like
I take 3 because I want to go to the third moment. So I need to take as many velocities that I can capture. So, okay, I have a naive idea, which is wrong, okay? So I need up to third order moments, so I take 3 speeds, right? Let us try out whether this works. You should know that it does not work because we start with a 0 order moment, right? So we would have to have 4 probably, but I don't know. Let's try out. Yeah? So particles move with these integer velocities, which means that the populations, so populations is how many particles or how big the probability on this particle is they hop from node to node. On a regular grid, so the grids can be Cartesian or, for example, hexagonal, but here it will usually be Cartesian. So the important thing is particles are not split up. They always come from one lattice node to the next lattice node. Yeah, this is why they have this. They have to have this particular speed, and the distance has to be, the distance between the nodes has always to be the same, and the time step always has to be the same, right? So, and then they have the collision. So particles interact with each other on the nodes. And this is supposed to conserve or that the conserved moments will stay here the same. So this is what it means to be conserved, and the non-conserved, they will change in a fashion that we have to determine. So now we have to, so far we have only determined moments of continuous distribution functions. Now we have to deal with moments of discrete distribution functions. So we have M. So this is not the Mach number. This is M index A. Yeah, one-dimensional. So we have, of course, this integral from minus infinity to infinity over this discrete distribution function. So how would we write the discrete distribution function? Discrete distribution function is a sum of the discrete populations Fi, and they are located at IC minus Xi, and this it comes in with a Dirac delta function. So you know what a Dirac delta function is, right? So, and this has to be integrated over Xi A, and then we integrate over Xi, which now comes without vector because it's one-dimensional. Now what happens if you take an integral of a Dirac delta function? It is 1 when the integral includes this position and otherwise 0. So basically we end up having the sum over all the different directions Fi IC to the power of A. Yeah. So by the way, so simply the integral in the discrete version becomes a sum. Yeah, this is not so surprising. So now see whether 3 speeds are enough for having 3 moments. So let's see we have to start with a 0 moment. So the 0 moment is the sum over IFI CI by the power of 0, which is F minus 1 plus F0 plus F1, where we say that where we define this over bar as minus 1, this is something that's called comes from Miller indices. So Miller indices, anybody here studied anything together with crystallography or material science? So in material science, so there's crystals. Crystals are lattices, and they have a way, of course, of describing directions in lattices, which is called the Miller indices. And it is also useful to apply this nomenclature inside the lattice Boltzmann method to describe lattices there. Yeah, because otherwise, and if you look into books, somewhere, I'm wasting probably a little time. We take a little bit more time today potentially, but anyway, I should tell this. When I came to my lab, where they were doing lattice Boltzmann, even where I arrived there, they were already doing lattice Boltzmann, and all of the PhD students had a cube on their desk. And that on this cube there were a lot of numbers, and these numbers so there were different people in the lattice Boltzmann world had written different papers on different lattices, and they all used one index in an arbitrary order, to the different speeds. So everybody needed this cube in front of their desk to see what direction has what number, and then I told them, look, guys, because I come from so what I studied was semiconductor stuff, so dealing with a lot of crystals there, silicon and whatever. And I told them, look, guys, 200 years ago, crystallography has solved this problem. There is you don't need this cube in front of you. There is one way to describe this all the time. So, you know, if a few weeks later, all these cubes had disappeared, and we all agree what direction is what, yeah, by using as many indices as we have directions. Now, since we have so we are not counting these directions 0, 1, 1, 2 or something, but we go, so this is going negative, this is going positive, and when we have more dimensions, we'll have more indices, right? Okay, Miller indices, right. So this is the 0 moment. Then we have the the first moment. So the first moment is then, so what you're changing is the exponent to 1. And what this gives you is minus 1 plus 1 and none of the 0 parts. And in principle, you have to multiply this by c, but we'll get rid of the c because we'll assume that the c is equal to 1. So then at the third, you have m2. So m2, you take this to the second power. So then minus 1 to the second power becomes 1. So what you end up with is minus 1 plus 1 times c squared. And now this can go on. For example, the third one is, now see, this I is either minus 1, 0, or 1. Yeah? So you will now see a repetition, because if you take I to the third power, it's the same as to the first power. So we'll have minus this and this. The only thing is that for dimensional consistency, there would be a c to the cube, but we assume this thing is 1, so actually the numbers are the same, okay? So, and this goes on to m4, so this will behave like m2, so we'll have exactly the same thing, just this consistency here. Okay, so now you see there is only a finite number of these moments being independent of each other, and it's not very surprising that this number is exactly 3. I mean, we come in with 3 populations, with 3 directions, and we come out with 3 independent moments, and after this we say a repetition. Yeah. Now, so these things here, they are called, these are moments that already have a different name. This is why we call this aliasing, moment aliasing. And as a German, I'm never aware of what is the right pronunciation of aliasing. Who is for aliasing? Who is for aliasing? Who would pronounce this completely different? Okay, we go with aliasing then. Okay, good. Okay, so we call this moment aliasing. Remind me if I do it the other way. So you see, the thing is we have 3 discrete velocities. We end up with 3 independent moments. So now we have a problem. Yeah, my idea to use 3 velocities just to get to the third order moment was not successful, because we ended up with the second order moment as the last one that is independent. Yeah, and we have seen through the hard work that we did yesterday that for the Navier-Stokes equation, we need up to third order moments. So what we needed is M0, M1, M2, and M3, which is, of course, 4 different moments. Now, the moment M0 is, okay, I have been criticized for being inconsistent, and this is, of course, good. So, but I'm used to the sluggishness of the lattice Boltzmann world in this. Yeah, so the mass, because the zero order, is the zero order moment the mass or is it the density? So it depends on whether you associate your integral with the certain volume occupied by the lattice nodes, and whether you take this into account or not, you end up with it being mass, the mass there, or the density when you divide this density by its volume. So because we are sluggish, we are using the same word for both, which is one is actually an extensive and the other is an intensive quantity. Yeah. But anyway, so M0, mass or density. Density, of course, saying that mass is conserved is you get much easier through the physics guides. Yeah, if you say mass is conserved, than when you say density is conserved, because density is difficult. So M1 is momentum. Momentum is, of course, also conserved. And M2, what is M2? Energy. Now, a trick question. I announced that this is a trick question. Is energy conserved? Total energy? Yeah, but the moment is total energy. You know, we are in one dimension, so there's nothing else. This is the total energy. Now is this conserved? Why is this a trick question? I mean, it depends. Whatever your answer, I can say it's wrong. So, I mean, according to physics, according to the Boltzmann equation, energy is conserved. Yeah. Now we want to solve the Navier-Stokes equation. Does the Navier-Stokes equation conserve energy? No. You see, we approximate the Boltzmann equation at the level of the Navier-Stokes equation, and the Navier-Stokes equation indeed does not conserve energy. So what you can do with the Navier-Stokes equation is you can add an energy equation, yeah, and in this energy equation you can balance out the energy that you drain due to viscosity, for example, and put it into the thermal energy. You can do this, but the Navier-Stokes equation by itself does not care about energy conservation. And therefore, energy is not conserved according to the Navier-Stokes equation. So, and this is related here to our assumption that we had that T assumed to be constant. If T is not constant, we have to find an equation for T. Yeah, so I mean you would have to add another model for T. Yeah, so and that the temperature will rise, for example, due to friction. Yeah, and then we would see energy being conserved, but this is not what we built into our model. So at least this means we have one of our moments that we can change, because if M2 would be conserved, then all the moments would be conserved, then collision was not allowed to do anything, right? So then particles would only fly through each other, and then you could not adjust anything here. Okay, so this leads us now to the discrete equilibrium. So discrete equilibrium, now we are kind of back to is it mass or is it density? So the lattice Boltzmann nomenclature presents this as being the density, meaning it's the mass on that volume that we occupy. Yeah? Therefore, the zero moment is presented as the density. The first moment being conserved always means that the equilibrium is equal to the moment itself, would be the momentum, so it's rho times u, and the second moment is rho times, now there was this kBt, now the kBt is condensed kBt by m. So now this is condensed into being the speeds of sound squared plus the speed of sound plus the speed squared. So, and now we are in this trouble that we had this third order moment, which I believe we had also calculated yesterday in equilibrium, which is 3 times u rho cs square plus u square. Now the problem is we don't have this guy independent, right? So we cannot adjust this because we have this aliasing. Aliasing that M3 is equal to M1, and we can multiply this by C square, which we always assume to be 1. And now we look like we are a little bit in trouble because this here is not this here, right? Question is, can we make this here being that here? Okay, there's two things that we can do. Is the first thing is saying that velocity, we look only at small velocities. And if we look at small velocities, we can simply assume that u cube is 0. And when u cube is 0, then, okay, we make a mistake by this, but the mistake we decide that this mistake will be acceptable. And we also use here c equal being, so this is our velocity scale. We also assume that c is equal to 1. So this, please. A bulk velocity, yeah. What you mean by bulk is the velocity. U is what we have in the Navier-Stokes equation, yeah. So the primitive variable, yeah.
Why primitive variable cube has to tend to 0? Physically it's
Yes.
So if I cube it, it will be 8. So I cannot just.
Yeah, you have to assume that the velocity is small. I mean, if the velocity is so, what's okay? So you first of all you have to give. Okay, it is in so far different from the Navier-Stokes. I mean, it is the velocity in the Navier-Stokes equation, but it is given in units delta x by delta t. Yeah, it has to be given in units delta x by delta t. So, and this number in units delta x by delta t needs to be small. So you cannot use this method with any velocity. Only with velocities that are small compared to 1 delta x by delta t. So now what is small? Say, I mean, usually we take stuff that is pretty large and consider it to be small, like 0.1 being small. I think this is not small, but say it is 0. Your velocity is 0.1 in this lattice units. So this is usually the fastest that you can run lattice Boltzmann with. Yeah, so this is the fastest velocity that would be acceptable. Usually would be 0.1, and in there, u cube would be 0.001, which now you can decide whether this is small for you. The thing is, you can decide yourself what is your interpretation of delta x by delta t. Yeah, so because you can adjust your time step. So you can adjust your time step such that your 1 meter per second is in lattice units 1 by the power of -5. Okay? I mean, if you make your time step very, very short, yeah, so you can simply say 1 meter per second in the real world is 10 by the power of -5 in lattice units. Then, if you take it cube, it will be 10 by the power of -15, and then it is small.
So before setting the problem.
Yeah, I think you should talk into, because there's a recording.
So before setting the problem itself, we have to multiply that with a small number, the physical velocities.
Yeah, you have to decide. You have to decide on your grid spacing and your time step. And if you make your time steps smaller, yeah, you make your lattice velocity smaller.
But somewhere you mentioned that delta x equal to delta t, I guess, and that is equal to 1.
Delta x, wait, yeah, okay. So this is the numbers. That is the numbers that we are using.
There.
So this is not 1 meter. Yeah, this is not one. We still, delta x still corresponds to, say, 1 millimeter. Yeah. So if delta x corresponds 1 millimeter, what you do in your computation, you assume that you have a grid spacing of 1. Yeah. So on our chessboard, yeah, we go 1 step, I mean, to the next neighbor, and in 1 step. So time always goes 1, 2, 3, 4, and space always goes 1, 2, 3, 4. It's all integer. Yeah? So now you, as the one who is setting up the system, have to decide what the distance between the lattice nodes and the time step correspond to. This is what you have to do. And now what comes out of your simulation is a velocity in the units delta x by delta t. And you have to decide what delta x and delta t is, and so that you can match your 1 meter per second to whatever numbers you have in the lattice Boltzmann method. But because of this aliasing, you need to make sure that your velocity is small enough in these lattice units.
So throughout the simulation, delta x and delta t would be same.
Yes.
But if you come to the physical space, if delta x and delta t are same, so you cannot you cannot use the non-uniform time stepping, and you cannot use non-uniform grids also.
You can, okay, so you can do, we'll come to this in one of the lectures next week. Yeah. So indeed, we use non-uniform grid spacing, and we also use non-uniform time. That's all practically done. However, on that grid, so you will have different grids, and in each of these grids, you always assume you're going to the neighbor. So you will have a different delta x in one position than in a different position. Okay? But within the neighborhood, it also will always be one step.
Yeah. But in that case, c will not be equal to 1, right?
The c will be, I mean, the c will be equal to 1 because you make because it's delta x by delta t, and if you make delta x smaller in the same way you make delta t smaller, then it will still be 1.
Okay, thank you.
Yeah. So I'm guessing. So officially we go until 11 o'clock. I think I will take the entire time today. Sorry, I have to catch up. Where have I been? Right. Non-conservative. No, so wait. I have to go to this place. I was just trying to write down that the speed of sound squared is this k Boltzmann t by m, and yeah. So okay, coming back to what we wanted to do, yeah. So we somehow have to agree that we can make the velocity small enough that u cube can be put to 0. That, by the way, there's also other ways of dealing with this, but we want to start with the simplest example that is possible, right? So we assume that u cube is 0. And then we still have 3 times cs squared times u, and here we have just u. And now we observe that just by setting cs squared to be c squared divided by 3. Yeah, because cs, our speed of sound, is of course a free parameter for us. Yeah, so we can set it to a value that we like, and now we set it to 1/3. And if we do this, we observe that this becomes u times rho, which it is supposed to be, right? So this implies that in order for this to work, we have to set the speed of sound at 1/3 c, square root 1/3 3. Okay, now when we did this, we want to transfer populations into moments. Now we are, from here on, we are using c is equal to 1, so that makes our life a little bit simpler. So we have m0 being f minus 1 plus f0 plus f1. m1 is F1 minus F minus 1, and M2 is F1 plus F minus 1. And this can now be solved for the populations F. To be F1 is M1 plus M2 divided by 2. F minus 1 is equal to M2 minus M1 divided by 2. And F0 is M0 minus M2. So now if we know the moments, we know the populations. And now we know the equilibrium. We know the equilibrium. M0 equilibrium is rho. M1 equilibrium is rho u. And M2 equilibrium is rho 1/3 plus u square. Now you have to forgive me. Yeah, you see now they all come without units, so you can simply add 1/3 to u square. Yeah, which physicists get, you know, the hair goosebumps. Yeah, seeing this. Yeah, but this is the way it is usually written down. So which means that if we plug these equilibria in, we get for F1 rho 1/2 u plus 1/3 plus u square. Again, physicists get goosebumps. We add u to u square, yeah, because they are dimensionless. F minus 1 xu is rho 1/2. So what's the difference? The difference is just that here is minus u plus 1/3 plus u square. And F0 equilibrium is rho 2/3 minus u square. So now we have determined everything that we need for our lattice BGK equation. And now we do this in 2 steps, namely in stream. So we have this Fi at the position x, which is now not a vector because we are in 1 dimension, plus I delta t. So this is, we're going 1 step to the neighbor. In the next time step is equal to a post-collision state. This asterisk indicates post-collision at this position here and to time at the time now. This is what we call the streaming operator. And then we have a collide. And in this collide, we apply the BGK operator. So we collide at position x and t. We say this is pre-collision x and t plus omega. Here we have the equilibrium at x and t minus the thing itself at x and t. And this we call the collision operator. So now we have Fi asterisk. This is what we call the post-collision. Fi without asterisk is the pre-collision distribution. Omega is the collision frequency. So, and then there comes some theoretical okay, do you have a question? No. Okay. Now what we are doing here is we're splitting up the Boltzmann equation into two parts, namely in a streaming and in a collision. And by this, obviously, we make a mistake because we have to make this strange decision. Do we do streaming first and then collision, or do we do collision first and then streaming? So in the Boltzmann equation, these things kind of happen at the same time. Here we're splitting them up, and by splitting them up, we are making something that is symmetric in nature, asymmetric, because you're doing two things at the same time, right? Or you do one thing first and then the other, or the other thing first and then the one. Yeah, that's not the same. So we make the thing asymmetric. Oops. And when we make an asymmetric splitting, our methods will be only first order accurate. And if you use first order accurate methods, you go to a scientific conference, you will get told that you're incompetent. You have to use at least second order methods. So how do we have this, do this second order accurate? So I did not say it, but I put a heading here that's called trunk splitting. Trunk splitting is a way to make splitting of operators, so if you have several operators, symmetric again, and therefore second order accurate. And the condition for this is to have time symmetry. So time symmetric operators have even order convergence which means they are at least second order accurate. So the question is, how can we do this stream and collide in a time symmetric fashion? And the way this can be done by adding 1/2 streaming in the beginning and say this is Fi x and t minus Fi, and now I introduce a new population S x minus I delta t. So we are moving this population now half a distance, yeah, in half a time step. Yeah, we put this to 0. Then we do the usual collision that we had before. Minus, oops, yes. I, x and t is equal to omega Fi equilibrium x t minus Fi x and t. And then we do another half streaming where now we generate this as FIS, and we do the other half of that streaming. Where the outcome of the collision is the input. And now this is, you could say, almost symmetric. If you look at the time sequence, now what is happening, you do 1/2 streaming up front, then you do a collision, then you do 1/2 streaming, then you do 1/2 streaming again, then you do a collision, then you do 1/2 streaming. Now the 1/2 streamings, now you can combine this here with this here, yeah? So you do half streaming, yeah? So this combines to a full streaming that we had before. So you had, in the beginning of your algorithm, you have a half streaming, then you have a collision, then you have a streaming, then a collision, then this can go on, yeah, to a next streaming and collision, and then to have a half streaming again. So interestingly, inside, so you still have streaming errors or you still have, either you have streaming errors or you have this half streaming in the end or half streaming in the beginning of your simulation, but everywhere else, what you do is just streaming and collide, and you are second order accurate anyway. Yeah? So this is, so to speak, not a change to the algorithm. So we don't actually have to split it up like this. But this explains the surprising observation that if we just don't care and do streaming and collide, we don't have the splitting error. We have the splitting error only in the beginning of the simulation and at the end of the simulation, and otherwise we are second order accurate. So this is we get no change to the algorithm. Yeah, because we can combine S back to Fi x plus I delta t half and t plus delta t half minus F after collision x minus I delta t half and t minus delta t half. So basically what you could also interpret this is that the populations that you deal with, they are not the populations at the collision time and at the nodes, but they are always in between collision time and in between the nodes. Yeah? So you read them from somewhere in between at half the previous time step, and you're writing them forward for half the next time step. Okay, now we want to see whether we actually solve the Navier-Stokes equation with this, and for this we do a Taylor expansion of this equation at x and t, call this equation 5.1. Yeah, so we'll take this here as our lattice Boltzmann equation, and we Taylor expand this. So we know that it is 0 because it's 0 here, and we Taylor expand at x and t, which means we'll first have this thing here, x and t minus post-collision x and t. So this is the Taylor expansion of this at this position, yeah? So you already recognize that this here is minus the collision operator. Now, these things here are not at x and t, but they are both slightly off, and the one is going in the one in positive direction and the other one is going in negative direction, meaning that we have to have this multidimensional Taylor expansion where we go to delta t half. So this is the amount that we are moving in time. So, and this into dt fi fix t plus fi x and t. So so you can see we get the plus because we have here minus, 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 and here we have plus, plus. Yeah, so plus, plus gives plus, and minus, minus gives also plus. So now we have here the sum. Plus, so we have to do this in the other directions too. So in the x direction, delta I half dx. Now, here's the same, plus, plus, minus, minus, yeah. So we end up with fix and t plus fi asterisk x and t. So these are the first derivative. Then there are also second derivatives. Second derivative in time is delta t square. Now we have 1/2 square times 1/2 from the Taylor expansion. So I assume you're all familiar with how Taylor expansion works. So the second derivative will 1/2 here, so it's 8, right? So, and this is then coming with the second time derivative, fi x and t. And now take care, because we now have a minus here, and we have this here squared, yeah? Which means now we end up with a minus here, fi asterisk x and t. So same thing for space. There will be an 8 here, dxx fi xt, again minus, important, x and t. So, and then we also have one mixed term. The mixed term is I delta t times delta t. Okay, I can write times delta t. So there is from the Taylor expansion for the mixed term, because it's twice the first order derivative, the first order term, there is no 1/2 here from the Taylor expansion. So it will only be the 1/2 times the 1/2, so it's a quarter. And here we have the mixed dx and t, and still we have here the same, because because minus, 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 so it is minus so it's minus fi star, and now this goes on with terms of delta t cube. Okay, so this is how the Taylor expansion looks like. And now what we do is we define an f over bar as the average between the pre-collision and the post-collision state. Yeah, because we don't really know which is the variable that we should use for our Boltzmann equation. Yeah, should we use the pre-collision or the post-collision? So my suggestion is we use the average between the two. We'll see why this is important and why this works. So we'll have this. This means we can also rewrite this as Fi being 2 Fi over bar minus Fi asterisk is equal to Fi half plus Fi over bar minus Fi asterisk divided by 2. So this here sometimes we'll find this here sometimes useful because we often see here that we have F minus F star. Yeah, so now we also have F minus F star. Yeah, and so this can be plugged into some places here. Okay, let's now look at our collision operator. Our collision operator basically looks like this. So after collision, though the population after collision minus the population before collision. So we've written that this previously was on the other side. I take this on the left-hand side. Is equal to omega Fi EQ. Now here was minus Fi before collision, right? So this Fi before collision I will now replace by what we have just discovered here and say this is Fi minus Fi after collision half minus Fi over bar. Now, okay, I just replaced Fi without collision with this. So now we have this Fi minus Fi star. We kind of have it on both sides. Okay, we have a switched sign, but otherwise we have it on both sides. So what we do is we bring it to the left-hand side, which gives us this 1 minus omega 1/2 is omega Fi equilibrium minus Fi over bar. So I took this to the other side, and then I like to have this here again standing alone. So I bring it back on the other side. It's 2 over omega minus 2 Fi equilibrium minus Fi over bar, and I call this the equation 5.2. So now this is something that this Fi. So this is the collision operator. This is the change that we make during the collision. Yeah, the change from before collision to after the collision. And now this depends now only on this F over bar anymore, right? So now we are plugging in this into our equation 5.1, where we have Fi after collision minus Fi before collision is delta t dt. Now you observe that here we had Fi plus Fi star, yeah, and in front we had this 1/2, and Fi plus Fi star 1/2 is this F over bar. We can directly write F over bar. Yeah, the same thing for I delta t dx Fi also over bar Now comes here the rest, delta t square over 8 dt. So this is the second derivative in time, fi minus fi star plus delta ti square divided by 8 in dxx fi minus fi star plus delta t square, not 8, it is 4 I dx t fi minus fi asterisk plus things of order delta t to the cube. Okay. Now there is one observation to be made. Everything on the right-hand side of this equation has at least one delta t in front of it, right? So this means that fi asterisk minus fi is of order delta t. So now you see the following, because this guy is reappearing here, and it's reappearing here. And we say this is delta t square, and we only observe until delta t square. Yeah? So this here is of order delta t, and it has also already delta t square in front of it, so it's actually delta t cube. The same thing here. So these things basically disappear. Yeah? So entering equation 5.2 for our collision operator here is fi asterisk minus fi. This is 2 omega divided by omega minus 2 in fi equilibrium minus fi over bar is then what remains, and what remains is delta t dt fi over bar plus dt I dx fi over bar plus what is ever left to order 3. So, and now if you want to rewrite this in terms of our Boltzmann equation, of course we take these things here to the left-hand side and divide by delta t. So we end up with dt fi over bar plus I dx fi over bar is equal to 1 over delta t 1 over omega minus 1/2 fi eq minus fi over bar. And this comes with terms delta t errors delta t cube. Now this is now the BGK equation that we are solving and compared to so there are two things of note here. One thing is that in the original BGK equation we just had this f here. So we were using f without any indication. We were using this as the pre-collision state. Yeah. Now we have this f over bar. F over bar is the average between pre and post collision states. This is something that we don't trace in the that is not a variable in our simulation. So in the simulation, we have the pre-collision state and we have the post-collision state. But of course, we can calculate the average if we like. Yeah, if we know both, we could calculate the average. But actually, it's not necessary to know this. It's only necessary that for the equation that we are solving, we are solving the Boltzmann equation for the average of pre and post collision. Yeah, indicated by this overbar. Another thing here is that we had this, the original BGK equation had this 1 over tau. Now, instead of 1 over tau, now we have delta t 1 over omega minus 1/2. And because I said the frequency, the frequency is kind of the inverse of the time step or the time. Yeah, you may have assumed that there would be just 1 over omega. However, due to this splitting that also led to this f over bar here, we now have a small modification to this. And this small modification is, so the tau, so what is the tau now? Tau is 1 over omega minus 1/2 delta t. So all we need to know, so we only need to know, right, that when we adjust our viscosity through tau, we do this by setting 1 over omega minus 1/2 delta t. That's all we need to know. And this correction was actually already known for the lattice gas algorithm, and it comes by a name, Eon. So even though I'm European, I may not pronounce him correctly. So this has been done in an obscure astrophysical journal written in French. This researcher discovered that if you have this cellular automaton splitting between streaming and collision, and then you have to redefine your viscosity in that particular way in order to get to the physically right value. Yeah. So he did this. I haven't ever seen the paper, so was not able to read it. So I think he did it potentially in a very different, with a very different derivation. But mathematics is consistent. So however you derive it, you will always end up in the same conclusion, of course. So this is the modification on viscosity that we have to do. Okay, I've taken a little bit longer, but it's still not 11 o'clock. That is the lecture for today. If you have any further questions, then please use the microphone because this is being recorded.
Sir, in equation 5.2.
5.1.
5.2.
5.2. So you mean, so 5.2 is actually the one up there. Yeah.
No, go a bit down. This is 5.1.
Oh, you mean this? Okay,
Yeah.
so now here, no, okay, so what I meant was I'm entering 5.1. Okay, so you're talking about this equation.
So the order of accuracy is t square, right? You wrote t cube. It's a second.
Because yes, yeah, okay, so you're completely right because we are dividing once. Okay. Okay, you are right. Sorry for confusion. Yes. See. Okay. So thank you for pointing this out. So we are taking this here, and we're dividing everything on this side by delta t, right? So then this delta t cube becomes delta t square, yeah, which still means we are second order accurate, and because we did this trunk splitting, we also expect that our method has an even order of convergence. Yeah. Therefore, yeah, thank you for pointing it out.
Can you explain the algorithm for one single time step?
The algorithm for one single time step.
Yes.
So this is a model of it. In reality, what we do is exactly this. Yeah. So okay, maybe I even go to the characteristic diagram. Okay, so if I may do some drawing again in my own picture here. So what you could assume now, this light blue thing is, say you have your population, so you have 3 populations associated with this node at that particular time step. But you could imagine them being stored there, there, and there, which means in between the time step and in between the lattice nodes. Yeah? Now you pick this population, and that population. No, okay. Okay, it's saying the incoming. The incoming would be, so okay, this, we are at this position, say, right? So here, all the arrows that are pointing to this node, yeah, they are collected. Now from them, we have to determine the conserved quantities because they influence our equilibrium. So we have to calculate the mass and the velocity. From the mass and the velocity, we can compute these guys here, right? Now we have mass and velocity, so we can execute the collision operator on these 3 populations on this node. Once we have done this, we send them 1/2 grid spacing away in 1/2 time step away. So we send this here, here, and here. Yeah, which is 1/2 grid spacing away and 1/2 time step away. And then in the next collision, they will pick them up again. And then we are repeating collision and streaming.
But there is no grid point at delta t by 2, right? And we are doing collision there at delta t by 2.
No, we are doing collision at delta t, and we do storing at delta t half.
Or we just store the values there.
Yeah, so here we store the values on their way. Yeah, so this we are storing these guys. Okay, see, this here we do collision, here we do streaming, here we do collision, and here we do streaming.
But you told that would be first order accurate if you do one streaming, one collision.
Yeah.
But we are aiming for a second order scheme, right?
Yes. Yes. So this.
I think it would be more clear if you just give the algorithm.
No. From the algorithm, it's not clear. Okay, so you have to imagine that this splitting. So let me think about this. So Lattice Boltzmann has been around since 1990 or the late 1980s. Yeah. So that this splitting was understood in 2014 or maybe 2010. Yeah. Okay. So it took 20 years for clever scientists to see this looking at the algorithm. So maybe you don't see it right now if you look at the algorithm. You don't see from the algorithm that it's second order accurate. This is a discussion that has been going on for 20 years until people came to a conclusion. Yeah? So the thing was, the algorithm does not look second order if you run the algorithm and you measure the convergence, it is second order. Yeah. So you don't see this by looking at the algorithm. This is so you see this from the fact that you can write the algorithm in this way here. So you can say that you do half of the streaming. So basically you store your data in between the grid nodes at half a time step. Yeah? Then you collect them from everywhere, do the collision at the full time step, and then you store them again at half their way, yeah, half time step later. Which means then you have a half streaming before, then you have a collision and a half streaming afterwards. So now this setup is symmetric in time. Because it is symmetric in time, it is second order accurate. Because it can have only an even order of error. Yeah? So, however, you can also see, when you just look at the algorithm, that you can combine this streaming afterwards with this streaming there. Because now you have half streaming, collision, half streaming, collision, half streaming. Now what you do with this half streaming is you do half streaming, you do one streaming. Yeah? So then this becomes the algorithm that is CS, yeah, all the time. You actually have an error, but only at the initial conditions and at the final condition. Yeah, so but these errors, first of all, you can calculate them and eliminate them explicitly, and second, they do not stack up, because you have them only at the end, at the both ends of your simulation. You have the error, no stacking up of this error. So therefore, if you just look at the algorithm, you would assume that this algorithm is first order accurate. Yeah, because it looks like you're doing Euler forwards. Yeah, but you're not. There has been 20 years of discussion saying this is Euler forwards. So how can it be second order accurate? Yeah, the reason is it is actually not Euler forwards, but you can reformulate this in a split up way. Yeah, and because you can reformulate it in the split up way, it needs to be second order accurate. The good thing is you don't need to do it this way, because you can just, if you stream half and half, you can put this together and you get a full streaming. This is exactly doing the same thing. So you do not pay anything for this. You're paying the same thing as if you were using a first order accurate algorithm, but you get a second order accurate algorithm.
So we are restricted.
Microphone, please.
So we are restricted to a second order accuracy. We cannot increase the order of accuracy.
It is not straightforward to increase the order of accuracy. It is so you can not in the same way. So if you want to increase the order of accuracy, you have to do it in a different way. Yeah, so you have to deal with relaxation rates somehow. Yeah, it's not like in a Runge-Kutta method that you proceed with the Taylor expansion and then you just add more terms and then, because okay, so what it has in common with the Euler method is that this is a fully explicit method that does not use any in-between steps. So if you have a Runge-Kutta method, yeah, so you have an Euler method, you just use the previous step and you go to the next step. If you want to have second order accurate Runge-Kutta, you need to calculate an intermediate step.
Yes.
And you want to go higher order, you have to go more and more intermediate steps, right? Lattice Boltzmann does not use any intermediate steps, but it still gets second order accuracy, yeah. But then it only gets second order accuracy without using any intermediate steps. So you could potentially also do intermediate steps to get it even higher order accuracy, yeah. But this is not what you're doing. So I mean, there is another way, namely, and we'll learn on Monday. We discuss about asymptotic analysis. So you can analyze your method in detail and see how the error depends on your free parameters, and then you can adjust the parameters that the next order disappears, and this is a way how you could get to a higher order. That's a pretty complicated procedure, but this has also been done and also led to a higher order of convergence. So it is not impossible to get Lattice Boltzmann to a higher order of convergence, but so from the ground state here, so how it's perceived, it is second order accurate.
And one final question. So we are considering 1D, right?
Yes.
So we have grid points along X,
Yes.
assume, and we have taken 3 discrete velocities.
Yeah.
Is it because, so what I'm assuming is the particle, either it can stay there only,
Yeah.
or it can move one delta x in x, positive
Yeah.
x, and one delta x in negative x.
Yes.
Is this the reason why we have 3 discrete velocities?
Yeah, that's the assumption. So we have three velocities, because 3 velocities is the smallest number of velocities that are required to get the Navier-Stokes equation, if there is something like this in one dimension, yeah, that has enough moments. So because you saw we need to go to the third order moment, yeah. Now the third order moment is, we don't actually have the third order moment as a degree of freedom, but we know that we only need the equilibrium thereof, and the equilibrium thereof is by aliasing, yeah, related to the first order moment. Therefore, we need at least these 3 velocities. So you can, of course, add more velocities.
No, how can we physically add more velocities? We just have 3 points, right? One grid point is surrounded by only 2.
You add more velocities by particles moving further than the next neighbor. So they can move further. So they can go to you can, in theory.
So ideally stencil becomes bigger and bigger.
Yeah, then the stencil, okay, so you could add to this a velocity like this and one like this. Yeah, so then you would have neighbors. Actually, you would have more neighbors, more velocities.
Okay. Thank you.
That's possible. So now we got actually above 11 o'clock. I don't know whether everybody we booked this room only until 11. Yeah, but anyway, if you please ask questions. I came thousands of kilometers for you.
So towards the last part.
The last part.
So you have the order delta t square.
Yeah.
Coming from the top, like 5.1 gives. From there, so
Yeah.
you are you neglecting delta t square terms out of it?
Yeah.
So then it is order delta t square accurate from there onwards, right? Then when you divide throughout by delta t, you should get an order delta t in the last step, isn't it?
I did not get your.
So in the first line, 5.1 gives.
You mean here?
Yeah, there. So you have that first term is order delta t, and then you have delta t square times, which
Yes.
is second
So
derivative
you mean
terms.
this one?
Those terms.
Yes. So, okay.
where
So
they went?
see, this is order delta t. Yeah. So then it's order delta t cube, because it's order delta t times delta t square. Right? Yeah. So this is why these two are absorbed into this.
So the second order accuracy is in the variable f bar, right?
In the what?
In the variable f bar.
F bar.
So if you take f or f star, you should get order delta t, right?
Yeah. So okay. Yes. So if right. So it is second order accurate for f bar, but it would only be first order accurate for f. Yes.
So what we going to do is that solving for f and f star, but finally we will calculate f bar, then compute the moments.
So now finally we are interested in velocity and pressure, and velocity and pressure can be calculated from f or f bar. So we don't see that this f bar is a theoretical thing that we determined to see in the simulation. We never use f bar. Yeah. So we use this here in analysis so that we can see that we are actually solving the equation more accurately than it looks like we are solving them. Yeah, because you see this usually if you solve something first order accurate, then what you expect is that errors would pile up over time. Yeah, but this f without overbar is always linked to this f with overbar. So in principle, it's only first order accurate, but the error that it has simply comes from the start up here. So it has a first order error, but this first order error is always the same. Yeah, and therefore because we don't have this pile up of errors, we can, when we do the proper post processing of this, and we set the viscosity in a proper way, we actually get the second order accurate velocity results, even if we never look at f over bar directly. Okay, I'm not sure that somebody wants to enter here. So, but anyway, we do until we. I mean, anybody can run away now, right? Somebody. Oh, you had a question?
I have a question.
Okay.
So, can you come down? So, what would be the implications if 1 over omega equal to half?
1 over omega equal to half.
Then tau would be 0, right?
Then tau is 0, right?
So, are we solving what do you call advection equation without diffusion?
So the implication would be that diffusion is 0.
Yeah, that's what.
Yeah. So so this will not be stable.
Oh, if in that case, then
I mean this what's okay. The implication of a BGK operator with tau equal with this being 1/2 would be that you have no build up of viscosity. This means that you are back to this time symmetry. You have eliminated the ether theorem, which means your simulation should run forward and backward the same in time. And remember, we've just shown we have a time symmetric operator. If we have a time symmetric operator and we add no viscosity, then what you are doing is you would run the simulation in backward. Yeah. So this needs to be unstable. I mean, it's a difficult physical, you know, this means it does not lose memory. This would mean it will remember its entire history. Yeah. If you put omega to equal to 1/2, it's omega equal to 2. Yeah. And you run it 1 billion time steps into the future, and then you reverse all directions and run it 1 billion time steps back, you must end up with the initial conditions, whatever they were.
So then how
Exactly.
then in that case, if I want to simulate just a Euler flow without diffusion,
Yes, but this is
what would be the procedure?
yeah, that's Euler. That's not possible.
So
Euler is not possible in
BGK.
The Euler equation is a strange. The Euler equation is a time symmetric equation. So temporal resolution of the Euler equation is kind of dubious thing. If you run the Euler equation backwards, you end up with the initial conditions. Now, usually this is not possible. Yeah, so because, this is from, the Euler equation is ignoring entropy, is ignoring information loss. Now we are getting into difficult philosophical questions here, yeah? This is, the thing is, if you put tau equal to, if omega equal to 2, then you, what you want to do is you want to press infinite information into finite memory. If you try to do this, this will always lead to the system to crash. Yeah? It will simply be unstable. So in order for this to be stable, omega always has to be slightly smaller than 2. There always needs to be some viscosity, some entropy production.
So this method cannot be applied for high Mach number flows, because there also viscosity will be very small. Viscous effects.
No, yeah. So it can. Okay, so I did not say that it cannot be used for small viscosity. Your question was, when omega is equal to 2, then there is 0 viscosity.
Yes.
That's a difference. It is a difference between small, small and 0 is a difference. Yeah, this is a small Euler equation, and okay, so this is a big mystery that the if you make the system larger and larger and larger and larger, or viscosity smaller and smaller and smaller, the result of the Navier-Stokes equation for smaller and smaller viscosity, higher and higher Reynolds numbers, is not the solution of the Euler equation. Yeah. So you have this contradiction. There are 14 minutes over, but anyway, we have this strange contradiction. If you take the Navier-Stokes equation and you let the viscosity go to 0, you end up with the Euler equation. But if you take the solution of the Navier-Stokes equation for smaller and smaller viscosities, this solution of this equation is not the same as the solution for the Euler equation. These things are fundamentally inconsistent. So it is a difference if you ask what happens when the viscosity is very small and what happens when the viscosity is 0. Yeah, the viscosity can be small, but it cannot be 0. If it is 0, then you lose the error of time. Then if viscosity is 0, then your equation becomes invertible. Actually all of this, the arrow of time and the discovery that the world is made out of atoms, all of this lingers on the presence of viscosity. Yeah, viscosity is proof. So in a continuous world, you don't have viscosity. In a symmetric world, you don't have viscosity. So that the observation that there is viscosity, yeah, breaks down this symmetric, the symmetry of the universe. Yeah, viscosity breaks the symmetry. Because of viscosity, we know that time goes one way. Yeah, and in the very moment this thing becomes zero, then there is both ways look the same. Yeah.
Okay, thank you, sir.
So there was, sorry for this philosophy. Do you have?
Sir, if omega is less than 2,
Yeah.
if omega is less than 2, then omega is less than 2.
Omega is less than 2.
So
yes.
then what is the stability of BZK operator like?
So this depends a lot on your collision operator. Yeah. So you want to get with viscosity with omega closer to 2, much closer to 2. So we'll have in the next 2 afternoon sessions, we'll introduce some lattice Boltzmann code, first with BGK operator, then with different operators. And then you see that you can get omega closer to 2, the more work you spend into the stability of this method. And actually, when we talk about high fidelity lattice Boltzmann methods, what we mean is that we talk here especially about lattice Boltzmann methods that allow us to go with omega very close to 2, yeah, so that we can actually get to high Reynolds numbers flows. Yeah, so I mean we can have omega. So for BGK usually we can go with omega maybe 1.9. When you use cumulant methods, you can go with omega to 1.99999 something. Yeah. So this is, I mean, you get pretty close to 2, but you don't get 2. That's 2 is not possible.
Okay, then how does matters if simulation start with collision? Now, if you have initial conditions, we have if you start with collision or if you start with streaming, so it does matters
It depends on what you set as initial conditions. Okay. I mean, you can start with collision, and then, I mean, you will. It all comes down to your initial conditions. You can set initial conditions for starting with collision, and you can set initial conditions for starting with streaming.
Okay, it will give the same results, you're saying. At the end,
no, I mean, no. Yes, if you give the same initial condition, then it will give you a different result when you start with streaming or with collision. So when you set your initial conditions, you need to know whether you start with collision or streaming. Yeah.
Like how do you know
how do I mean, I write the code, so this is how I know.
Okay, it depends problem to problem, you're saying
It's
depend to problem to problem.
No, what do you mean? How to set the initial conditions?
Yeah.
The initial conditions, of course, depend on the problem.
If someone wants to start with collision, not for streaming.
Yeah, so then this person would have to set their initial conditions for F and not for F star.
Okay.
Yeah? So that's, we will have a lecture on initial conditions on, I don't know when, on Friday. On Friday we have it. So, guys, we are 20 minutes over. Any further questions? So this afternoon, I I think there's no other message. No. In this afternoon, we'll have the first practical session on looking at the code and the let me see, the first coding tutorial on the equilibrium. This is what we have this afternoon. So please all attend. So this is of course much more interesting than what I'm the long integrals and difficult stuff that we do here. Okay, see you then.